Yesterday we learned two new things. One was what we call the hand rule for deflection, or we'll just shorten it and call it the deflection rule. The deflection rule is used to find the magnetic force acting on a charged particle that was moving through an external magnetic field. The other thing that we learned was an equation. The equation was used to find the magnitude of the magnetic force acting on a charged particle moving through an external magnetic field. Now, let's go back and review the deflection rule for a second. This was quite a bit different than the first two rules that we learned. Remember the wire grasp rule, thumb, bent fingers. The coil rule, bent fingers and thumb. The deflection rule involved three variables. There was the thumb, there was the straight fingers, not the bent fingers, but rather the straight fingers. And the third variable was the palm of your hand. The straight finger, the thumb, just like in the wire grasp rule, is used to point in the direction of the moving charge. So it goes back to that first rule that we learned here a week or so ago. We say the thumb points in the direction of the moving electric charge. If it's a moving negative charge, use your left thumb. If it's a moving positive charge, use your right thumb. Now, the straight fingers are different than any of the other rules. The straight fingers are not bent, hence they're straight. They're used to point in the direction of the external magnetic field. What do we mean by that? First time we've seen this, right? With the coil rule, we had a magnetic field generated by the coil. With the wire grasp rule, we had a magnetic field generated by the moving electric charge. We still do have a magnetic field generated by the moving charge as it moves through an external field. But the external field is not that field that's produced. That external field is the field that was already there. It was caused by something else, maybe a couple of bar magnets, maybe the earth, or so on. These straightened fingers point in the direction of the external, and I'll underline that because there are two magnetic fields. We want it to represent the direction of the external magnetic field. So if we have a charged particle moving towards the left, towards the east, we'll say, for you guys, and then we have a magnetic field pointing towards the north, we're going to say thumb towards the east, straighten fingers towards the north. My palm will automatically point in the direction of the magnetic force. In that case, the one that I just gave you, we would say thumb to the east, fingers to the north. My palm would point downwards towards the earth. That would be the direction of the magnetic force. The equation that's used to describe the magnitude of that magnetic force we learned yesterday looks like this. F is equal to Q. What does Q stand for? Charge in coulombs times V, speed, times B, the magnetic field strength in Tesla. Now, we also, if we want this to look like it does on our data sheet, we also put a little upside down T underneath the V. What does that mean? It's perpendicular. This equation, as I have it written and as it appears on my data sheet, is only valid if V is perpendicular to B, if the charged particle is moving perpendicular to the magnetic field. There is a way to find the magnetic field, the magnetic force strength if they're not perpendicular, but we don't have to worry about that. If it's perpendicular, the magnetic force is QVB, and we can find the direction of it using the deflection rule. I'm going to put a circle around these and make a little note above it to say that both of these, the deflection rule and the equation, as it's stated right here, the specific form of the equation without the sine theta, as it's stated right there, are only valid we're going to say they're only valid if the charged particle is moving. What does this mean? If Q is moving perpendicular to the external magnetic field. Now, there is one more scenario that we can deal with, but it's easy. If the charged particle happens to be moving parallel to the magnetic field, what's the direction of the magnetic force? What's the magnitude of the magnetic force? There is none. So there is no direction if there is no magnitude. Perpendicular, what you see inside the circle. Parallel, nothing. There is no force. What if it's not perpendicular or parallel? Yeah, not for us in Physics 30. That's when we tack on the sine theta on the end of this equation, but we're not going to have to worry about that in Physics 30. Next year, if you take a course in university in physics, you will see that. F is equal to QVB sine theta. Doesn't make it that much harder. We just don't do it, not because it's too hard, but because we don't have to do it. All right, what I want to do here now is a couple quick examples using the deflection rule, and then we'll do an example using the equation, which we didn't do yesterday. So let me draw a couple of these out. Let's say, first of all, we have a positive particle moving towards the right. Positive particle moving to the right side of the page. We have a magnetic field that's pointing this way. Listen carefully to the question. Listen carefully to the question. This is like RTQ, ATQ, except it's not read the question, answer the question. It's LTQ, ATQ. Listen to the question, answer the question. You got it? Here's the question. What is the direction of the electric force acting on this charged particle as it moves to the right? What is the direction of the electric force acting on this charged particle as it moves to the right? To the left? No. Into the page? No. Out of the page? No.
Down.
Down and to the right? No. Yep. No. Into the smartboard was the answer? No.
That's nice. Wait, is that a positive or is that a cross?
It's a positive particle. Yeah, it's a positive particle moving to the right through this magnetic field. We want to find the direction of the electric force acting on this charged particle.
Oh, that's stupid.
What's the answer?
Can't figure it out.
There is no electric force acting on this charged particle because it's moving through a magnetic field. If we change this, listen carefully, guys. If we change this to an electric field, then there would be an electric force acting upwards on it. Because the electric force acting on a negative particle is opposite to the field. Remember that from our last unit? I'm positive the force is with the field.
Isn't it a positive though?
Yeah, okay, so it would be downward then. You're right, it would be downwards.
like really confused.
That should have been downward because it is a positive particle. Remember, an electric field causes an electric force. A magnetic field causes a magnetic force. I had that drawn a minute ago with a magnetic field. A magnetic field will not cause an electric force. An electric force will not cause a magnetic force. Think of it in terms of gravity for a second. If I have a gravitational field pointing downward, which I do towards the Earth, right? What magnetic force does gravity cause? None, of course, right? What electric force does gravity cause? None. So why would a magnetic field cause an electric force? It doesn't. If I have an electric field, then there will be an electric force. And the direction of that force will be with the field because, remember from last unit, I'm positive the force is with the field if it's an electric field. But if it's a magnetic field, there is no electric force, but there is now a magnetic force. And we can find the direction of that magnetic force using the hand rule for deflection. We're going to say because it's a positive particle, you're going to use the right hand, right thumb in the direction of the particle, which is toward the right side of the page. My fingers are going to point in the direction of the, not the electric field, but the magnetic field. Thumb, fingers point downwards toward the bottom of the page. Palm points which way? Into the page. So the magnetic force is in the page. There is no electric force here because it's a magnetic field. But if I changed it to an electric field, there would be an electric force, and it would be with the field. Do you understand the difference between an electric force and a magnetic force? Electric force is easier, right? It's either with the field or against the field. Magnetic force is always perpendicular to the field. It's a little bit harder to deal with. Okay, let's try another one. Let's say this time we've got a negatively charged particle moving downward. A negatively charged particle moving downward. That's its velocity. This time we have a magnetic force not a field, but a magnetic force, not an electric, it's a magnetic force acting on a charged particle to the right. This time, we want to find the direction of the magnetic field. We've got three variables: thumb, fingers, palm. Usually we say, here's my thumb, here's my fingers, which way does my palm point? This time, since we have the force, we want to find the field. Let's say thumb, palm, which way do my fingers point? Right? My thumb is going to point down toward the bottom of the page. My palm is going to point, because that's the force, my palm is going to point towards the right side of the page. Thumb down the page, palm towards the right side of the page. My fingers, which represent the field, are pointing out of the page. You have three variables here, right? You have the thumb, you have the fingers, and you have the palm. You will be given two of them. Maybe it's this one and this one. Solve for the palm. Maybe it's this one and this one. Solve for the field, or the direction of the fingers, which is the field. Maybe it's this one and this one, and you're going to solve for the direction of the thumb. So three possibilities, right? You got direction of motion of the particle, the field, and the force. So you're going to solve for one of those three, given the other two. All right, I want to take a look at an example problem involving the math. It's also going to use the hand rule for deflection here. Example number one on the sheet that I gave you on the first day of this unit here over a week ago. It says a proton is moving at a speed of 5 times 10 to the 5 meters per second into the page through a magnetic field that is directed to the right of the page. What's the magnetic force acting on the proton? Is the particle moving perpendicular to the field? Is the particle moving perpendicular to the field? It is. Yes, it is. The proton is moving into the page. The magnetic field is to the right of the page. So we've got one going this way, one going this way. Those are perpendicular. If they weren't perpendicular, we better hope they're parallel. Because if it's not perpendicular or parallel, we don't know how to deal with it. Because it is perpendicular, what we've been learning for the last day or so is applicable here. We're allowed to use the deflection rule, and we're allowed to use the equation. F is equal to QV perpendicular times B. Q is 1.60 times 10 to the minus 19. V is 5 times 10 to the 5. And B is 2 times 10 to the negative 2 Tesla. When we multiply those numbers together, we fairly easily get 1.60 times 10 to the negative 15 newtons. I'm not finished. How come? Magnetic force is a vector. A lot of times you get a question like this that says, what's the magnitude of the magnetic force? If that's the case, I'd be done. This doesn't. This says, what's the magnetic force, which includes magnitude and direction. We've got positive particle going into the page. We've got a magnetic field that's going to the right of the page. We're going to say my right thumb goes to the right. My fingers go into the page, direction of the field. Thumb goes into the page, direction of the particle. Fingers go in the direction of the field, which is to the right. Palm's going to point, wrong hand. Using your left hand, it's a positive particle, yeah. Right hand, thumb, fingers, palm's going to point down the page. We'll say down the page, or we could say toward the bottom of the page. All right? Example number 2. This one we have to make a couple of changes to it because there was a couple of typos. The first part of it, we're going to say this particle with a charge of 1 times the elementary charge is not traveling out of the page, rather it's traveling east through a magnetic field that is pointing to the north. We want to find the speed of the particle that must be traveling near the Earth's surface in order to not be deflected. We also need a strength of a magnetic field. It should have been given to us a value of 6.00 times 10 to the negative 5 Tesla, which I told you didn't need to memorize magnetic field strengths when I gave you that table earlier on in the unit. But if you do happen to remember orders of magnitude, this fits right in there with a typical magnetic field strength for Earth. Okay? Not that you need to know that necessarily, but it does fit in there perfectly, right in the middle there. We want to find that the speed that the particle must be traveling near the Earth's surface in order to not be deflected. This is a perfect question to illustrate seeing big picture, not looking for a specific equation to answer a question based on givens. We got to look at what's going on here. Okay, what's going on? We got a charged particle that is near the Earth's surface that is not being deflected up or down or left or right. We know it's moving through a magnetic field. Therefore, if it's moving perpendicular to a magnetic field, it will experience a magnetic force. Why is it not being deflected if it's experiencing a magnetic force? Okay, this is what you got to be thinking about here, right? Not just, oh, here's my numbers, here's my givens, let's set them into an equation. This is what we got to be thinking about in this question. Why is it not being deflected if there's a magnetic force acting on it? There's got to be some other force that's balancing it. Right? If something's going in a straight line and there's a force acting on it, there better be another force to cause that first force, to be balanced. And of course, it stands to reason that when you're near the Earth's surface, then it's going to be the force of gravity that's going to balance it. Make sense? I got a little note on here at the back that I put earlier today. The word undeflected in our little physics dictionary / thesaurus means balanced forces. It may be an electric force equals a magnetic force, or an electric force equals gravity. In this case, it's the magnetic force equals the gravitational force. This is the thrust of that question. Fm equals Fg. Givens are important. It's important to recognize what our numbers are. But what's more important in this question is to recognize what's going on. Okay, big picture. Two forces must balance. We're going to say Fm is equal to QVB. That's valid because the charged particle is moving perpendicular to the field. And we're going to say Fg is equal to m times g. By the way, which way does gravity act? Down. Gravity always acts down, right? Let's just double check to make sure that magnetic force is acting upward. It better be, otherwise there's a big problem with this question. We've got a charged particle, positive charged particle, so right hand, moving to the east. Okay, that's north, that's east. Charged particle moving to the east, magnetic field going to the north. Which way is the magnetic force? Wrong hand. Yeah, the magnetic force is going up. So gravity was down, magnetic force is up. Okay, we're good, right? These two forces could balance each other out if they're in opposite directions. Okay, let's solve for V here. The mass is 5 times 10 to the negative 25 kilograms times G, which is 9.81. We're going to make that positive because it's not really the forces that are equal. It's the magnitudes of the forces equal. We're making them both positive. If one is 10 up, the other is negative 10 down. But we're setting the magnitudes equal, so don't worry about direction at all here. Q is 1 elementary charge, or 1.60 times 10 to the minus 19 coulombs, times the magnetic field strength of 6.00 times 10 to the negative 5 Tesla. Now follow along with me on my calculator here. I'm going to make a mistake. Don't type this out according to the way I am yet. I'm going to make a mistake on purpose. I want you guys to see if you can catch where the mistake is being made. Once we do that, then I'll type it in the right way, the way you should enter it in, okay? So follow along closely. We're going to say 5 times 10 to the minus 25 times 9.81. Is that okay so far? Yes. Divide it by, use some brackets here, 1.6 times 10 to the minus 19 times 6.0 times 10 to the minus 5. I get an answer here of 1.8 times 10 to the minus 9, which is the wrong answer. What's wrong with the way that I entered that into my calculator? Today? You could put brackets around the top part, but you know what? That wouldn't change anything, actually. It certainly wouldn't be wrong, but it wouldn't change anything. Nicole? Yeah, I put brackets around each number on the bottom. The way that your calculator interprets that is that we've multiplied 5 times 9.81, divided it by 1.6, and then multiplied the whole thing by 6 times 10 to the minus 5. This is the way we want to enter that. 5 times 10 to the minus 25. Janae, was it you that said we should put brackets on the top? Yeah, we absolutely could, but we don't need them on the top. Multiply that by 9.81, divide it by, now let's use brackets, but let's put the whole bottom in brackets. 1.6 times 10 to the minus 19 times 6 times 10 to the minus 5. See the difference? It's a small difference, but look what happens. We get 5.11 times 10 to the minus 1. It's a pretty small speed. The reason that's so small is because, listen, it doesn't have to be going very fast to balance the gravitational field, because we learned in our last unit that gravity is actually a pretty weak force, right? So the magnetic speed doesn't have to be very high in order to achieve a magnetic force that balances that weak gravitational force, especially for such a small particle like a 10 to the minus 25 kilogram particle. Usually, we get a speed of a charged particle that's faster than this, but in this context, because it's balancing gravity, it's going to be small. All right, we're going to give you a break for a couple minutes, and when you come back from that break, I'd like you to take a look at worksheet number 11. You've already done questions 1 to 8 on that worksheet. I'd like you to finish off that worksheet now, and that's going to be questions 9 to 12. So worksheet number 11, questions 9 to 12 when you come back from the break. Okay, let's plug forward a little bit and extend what we've just done. We've learned that there is a magnetic force acting on a charged particle that moves perpendicularly through a magnetic field. We can find the direction of that force by the deflection rule. We can find the magnitude of that force using F is equal to QVB. But let's describe what happens as a result of that force in a little bit more detail right now. What we're about to say doesn't change anything that you've just learned. It doesn't correct anything that you've just learned, because everything that we've just learned is correct. This is just providing more detail on it. We've got a charged particle represented by this little circle with a negative sign inside it moving to the right. We're going to say the velocity of the particle is red. It's moving to the right. There will be a magnetic force acting on this particle. We're going to represent the magnetic force by blue. Which way would that magnetic force act? Well, the particle is moving perpendicular to the magnetic field that is into the page. So we can say thumb in the direction of the particle, fingers would point in the direction of the field, which is into the page, palm points which way? Down the page, right, toward the bottom of the page. So the magnetic force is originally downward. Now, what happens to the motion of this particle as a result of its initial inertia going to the right and the force that's acting downward? Where's it going to go? Yeah, then good. Somewhere down and to the right. It's going to go down here somewhere. So now let's describe its velocity this way, down and to the right. And let's look at the direction of the force on it now as the particle moves down and to the right. Thumb down and to the right, fingers still into the page because the magnetic field hasn't changed, right? Palm points down and to the left. The magnetic force acts this way. Where's the particle going to go now? Somewhere in between, right? Which is downwards. Now we're going to put our left thumb pointing downwards, finger into the page, palm points to the left. The magnetic force is this way. Now the particle is going to, of course, go somewhere in between. We're going to say thumb in the direction of the particle, fingers direction of the field, palm points in the direction of the force, which is this way. What do you notice about that magnetic force? That blue magnetic force always points where? To the same spot. Where you have an object undergoing a certain type of motion, and the force is always pointing to that one same central spot, we call that motion circular motion, uniform circular motion. That's a whole unit of physics 20, uniform circular motion. We can still describe the force using the equation that we learned yesterday and spent a fair bit of time using today. We're still allowed to use that equation. What I've just told you doesn't change anything. It just adds to what you've learned. If you could solve questions 9 to 12 on worksheet number 11 using that equation, then you still can. It's still correct. But now we have an additional tool in the toolbox to use only if we need it. The other equation that we're going to describe this motion by is, anybody want to take a stab at this? No.
Radius.
Yes. What type of motion was this, did we say? Circular motion. How do we describe the force acting on an object toward the center of a circle? In any context, whether it's the Earth going around the sun or my keys being swung around my head on the end of a lanyard, the force that acts toward the center of the circle is called a centripetal force. The centripetal force. And that force is given by the equation mv squared over r. So we're saying that equation number 1 is absolutely still valid. Absolutely. Nothing has changed in that regard. But now, if we need it, we're also allowed to use this equation. The centripetal force is mv squared over r. Now, we're also allowed to, if we need to, combine the two of them. Fc is equal to Fm, because the reality is that centripetal force, the force that's causing this particle to go in a circle, is really caused by magnetism. If the centripetal force is caused by the magnetic force, then why couldn't we set them equal to each other? In other words, mv squared over r ends up being equal to qvb. So we're allowed to do that as well. Now, it's just a matter of whatever looks to be the most convenient. Whatever fits the givens the best is the one we're going to use. Number 1, number 2, or number 3. Now, I'm going to take you off to the side for a little bit here, just to point out that this equation, Fc is equal to mv squared over r, is not actually on your Physics 30 data sheet. But the equation A is equal to v squared over r. Centripetal acceleration is on your data sheet. And the equation A is equal to F over m is on your data sheet. So if you sub this into here, then we get v squared over r is equal to F over m. And then F is therefore equal to mv squared over r. So if you're going to want to use that equation for centripetal force, you either need to remember the equation or you need to set these two equations equal to one another and figure out what the centripetal force is. Tonight your homework is to finish worksheet number 12. You will not use this on worksheet number 12. You only use this if you need to. It's valid for worksheet number 12. It's just not helpful. The next worksheet that I'm not assigning for homework tonight will use this. All right? So your homework tonight is to finish worksheet number 12. And in addition to that, actually, was it worksheet 12 or 11 that we were going to? 11, worksheet number 11. And also, immediately after school, you're going to get practice question set number 16 posted as well. Complete both of those for tomorrow, please.